some tricky stuff. Now, really, it's the conclusion of this section that's the most important thing. But just give you an idea of how we could analyze these things. So when you have a differential equation, that's what this ODE means, there's two types of error. One is errors due to the nature of the technique. So for example, if you were to approximate, say, sine of x just using 4 terms, you're throwing a lot of stuff out, and so the method itself is causing error. Similarly, Euler's method is just using little bits of straight lines. You're getting errors from that. The other place you get error is rounding error. So like you use a computer and you want to put in 1/3, you can't get 1/3, say in VBA. You get 0.3 with maybe 16 trees. But there's a difference between 1/3 and 0.3 with 16 trees. And you say, it's not very much. It isn't, but if you're making 1,000 or 10,000 calculations, those rounding errors can add up. So we want to be aware of that, and we want to have an element of distrust of the output from the VBA. Okay. Now you can estimate the truncation error often. So this is numerical analysis. You have a method. In this case, it is Euler's method, and we can analyze the method and kind of say something about the error and the error due to the method not being perfect. So let's kind of remind ourselves of what we're looking at. So we've got a differential equation, dy dx, which is same as y dashed of x, is some formula in x and y. We've got a starting value of x and y. We've got a step size, and I think all we're going to focus on for the moment here, so that the distance between these is h. And we want to say, okay, if we use the Euler method, so there's some curve here in the background, something like that. If we use Euler's method to approximate the solution of this curve between x0 and x1, we want to say what is the biggest that the error can be. And ultimately, actually, we don't want an exact formula or anything like it. We ultimately want to say, what happens to that error when we change the step size? That's what we're really after. Okay, so this will be some heavy stuff, but we'll go pretty fast on it. Okay, so you can estimate the truncation error when using Taylor series. So that's why we did Taylor series. So if the solution to an ODE is sufficiently nice, which it nearly always will be, it'll be equal to its Taylor series. So this is the exact solution over here is equal to its Taylor series. Now, what you have here, the thing at the end, this sum goes on forever and ever and ever, doesn't it? So the Rn is that forever and ever and ever bit. So it's the difference between the exact solution and, say, the first n+1 terms. Okay, and you can show, let the pure mathematicians do it, is that this term, the difference between this approximation, the n+1 terms, and the exact solution, is equal to this horrific looking thing, the n+1 derivative of y evaluated at xi. Now xi is some point between here and here. Now we don't know what it is, it's just some point in there, divided by n+1 factorial by, I think this x actually should be, I'm going to throw in x1 here, and then I have to put them all x1s. Okay, and okay, there's a few things going on here, right? Look at this yoke. The difference between x1 and x0 is actually the step size. So if the step size is small, and we take it to the power of n+1, that's small. And look at the n+1 factorial. That's a big number if n is big. So if we take a lot of these guys on, say we get up to n equals 7, 8 factorial is like, I don't know, it's a big number anyway. I'm just messing around in my calculator now. Here we go. 8 factorial is 40,000. So if the derivative isn't that big, you're guaranteed that this will be small. Okay, that's basically what I'm saying. So this reads something like this. So this is just all I was saying, that if you're talking about x1, these things are h's. So the solution, this should actually be at x1 is equal to the starting y value. Here you've got the step size times the slope at the previous point, and then you can add way more of them if you want to get it more accurate, and the remainder term. So this actually shows, so the remainder term is roughly the n plus 1 derivative evaluated at some point over n plus 1 factorial, which gets bigger as n gets bigger, times h to the n plus 1. So this shows actually that if you want to use some of these terms, the more you take, so as n gets bigger, the difference between this polynomial approximation and the exact solution gets smaller and smaller and smaller. But of course, the point is, we're talking about Euler's method, which is just this bit. So the error is going to be big with Euler's method, because we're not taking loads of these terms. And we saw this previously, where we didn't have very good errors, or sorry, big errors. Right. So if we're using Euler's method, the true solution, y of x1, is equal to y of x0, previous point, plus step size times previous slope plus R1. And so you get that the true solution is equal to y1 plus one of these remainder terms, this R, and it's the R1. And you can show that there's some value, there's some xi between, if I use the formula on the previous page, the difference between the true and the approximation is R1, which is equal to the second derivative at some point in between x0 and x1, divided by 2 factorial times h squared. And what I'm going to do is, I'm just going to take the maximum of the second derivative. It's a worst case scenario, so we get something like this. And look at this thing. What is it? So the error is less than a multiple of h squared, order h squared. So if you use the Euler method, over one step, the error is order h squared. Half the step size will quarter the error, because the error is order h squared. On occasion, look, this actually isn't interesting, but you can find the exact place. It's just not important. I'm actually going to throw this bit out. It isn't typical that you can find this. So usually what we'll do is, so we know that, so this is, okay, so let's set up everything and just kind of make this a bit clearer. So use the Euler method to approximate y of x1. The error is equal to, for some xi, it's the second derivative. This little Greek yoke is tricky to draw. Oh, times h squared over 2. So, okay. So what we're going to do is, and again, this bit isn't too important, is we're going to say that this is, yeah, so I'm messing around with this second derivative, but really I only care that it's a multiple of h squared. But what we're saying is, I'm just kind of repeating myself here. So let's say it's the, there. So let's make this second derivative as big as possible. Taking the maximum of it, it's something like this. And it's easy to sometimes maximize the second derivative. But again, it's not that important. So what I'm saying here is, in this one, you can maximize that. You can find the biggest value of that and analyze it, but you don't care. Don't actually care. All I really care about is the h squared. So the error term for Euler's method is order h squared. It's a multiple of h squared. So if the second derivative isn't too big, having the step size will reduce the local error by a factor of 4. Now I might just do that just over here just to show you. Okay, so suppose you have the error, the original error is h0. Excuse me, step size. And so the original error, now this is going to be called a local error, so I just put the L there because it's over one step. Remember, we've Euler's method is loads of steps. It's less than or equal to some multiple of h0 squared. Okay, now if we change to, sorry, not twice, but half the step size, what happens to the local error? The local error now becomes h0 over 2 squared. And if you do h0 over 2, you get h0 squared over 4. So you end up with k h0 squared over 4, which is equal to, more or less, it's not equal to, but more or less, the previous local error divided by 4. So half the step size will reduce the local error by a factor of 4. If you go from the original step size to 1/10, it reduced the local error by a factor of 100. Okay. I'm not sure what this next little bit is going to be. Oh yeah, I think we're going to look at an exact example. So I think we need this example to talk about the difference in the local errors and the global errors. Right, so differential equation dy dx equals 6x plus 5, y of 0 is equal to minus 2. It's easy to show the solution is this. Okay. And therefore the second derivative, let's go to the second, well, actually you can get the second derivative from here. It'll be 6. Okay. So the error in using Euler's method here, or 1, is, so it'll be the second derivative evaluated at some funny point, divided by 2 factorial by h squared. But here the second derivative is 6 everywhere, and it's going to be 3h squared, no matter what the value of h is. So if h is equal to 1, this gives an error of 3. Halving this, it'll be 3 by a half squared, it'll be 3/4. So that's what we were saying. So we should focus on really just that it's a multiple of h squared rather than the fact that the 3 isn't so important. So the issue is, this is just measuring the error for a single step. And of course, we're going to do multiple steps. We're going to be interested in the global error. Now, I think we're going to show, and this isn't, there is some technicalities here, which I think will be alluded to later, but we won't worry about them. This isn't quite correct what I'm doing, but it's okay. So what we're going to say is, we're going to show that if you do it loads of times, and you look at the error at the very end, it's going to be actually a multiple of h. Okay, so let's see. So suppose you approximate solution of a differential equation between x0 and x n. Okay, so that means in particular, I'm going to use some notation here. So let's say L to be the length of this interval, xn minus x0. And if there's n points in it, then the step size will be the length divided by n. Okay, so that's the setup. So the global error, I want to get my notation right. At the end, actually, we forget about. is equal to the sum of the local errors. So you get the first error, local error, plus the second local error, and I'll explain what these are in a minute, plus the final local error. Now what's going on here is, so the first one is like, this is what we've been studying above, and this is, so you go from x0 to x1, this is the error. This is the error when you go from x1 to x2, and the next one is the error from x2 to x3, etc. Now what we're going to do is we're going to say that the absolute value of this global error is equal to the absolute value of this argument, by the way, is examinable, although is it appropriate? Maybe not. We'll talk about assessment in time. You can show that this is in fact equal to, you can show that it's less than or equal to, the absolute value of a sum is less than the sum of the absolute values. I said it will explain this a bit more at the bottom with an example with some raw numbers if you're a little bit lost. And what the hell is a local error? Okay, and now if this is, it says, oh, we're approximating, what I mean by that is using Euler. Now what we've shown in the analysis above is that the error in Euler's method, the local error, is a multiple of h squared. So what we can do here is we can say that each of these are less than or equal to a multiple of h squared. So the first one is, say, k1 h squared. The next one is less than k2 h squared. Less than k3 h squared. Okay, sorry, kn is the last one, apologies. Now take k star to be the biggest of these k's, so the max of the ki's. Then all of these individually are less than k star h squared plus k star h squared plus plus k star h squared, and there's n of them. Okay, so this is the global error. It's less than or equal to some multiple of h squared, but the thing is that the n here is, yeah, we want to kind of get rid of the n. Why? It's a little bit messy, we won't worry about that too much. But if we look at the h, if we look back up here, we know that h depends on n, you see. So you got n and h squared, you need to get rid of the n out of that. So put that into this, and you get the global error is n times k star, and h squared is, no, I want to keep the h, excuse me, my bad. So if you solve this, excuse me, for n, you get that, so multiply both sides by n, divide both sides by l, n, because I want to get things in terms of h, is l divided by h. So the n here is l divided by h times h squared. That's actually h, even though it doesn't look like it. And h squared divided by h is h. So you get l k star h. So what we've actually written eventually is that the global error, which we'll explain, is less than or equal to a constant times h. So what does that mean? The global error is of order h. So while the local errors are order h squared, so you can make them smaller. Like if you want to quarter them, you can half the step size. But the problem is when you half the step size, you've twice as many steps. And so even though you're reducing the local errors, there are way more of them. That's what this calculation is basically showing. So you end up only having, like, you don't really care about the error at one step. It's after all the steps, it's a multiple of h. So if you really want to decrease the error by a factor of 10, you have to decrease the step size by a factor of 10, which means, by the way, 10 times as many calculations. So that means it's not great. Now, I said here I'll try and explain this a little bit. And I do it with the help of this table here, okay? So what we have is we have some theoretical differential equation. dy dx is equal to some, depends on x and y. And in this case, the initial value of y at x equals 0 is 0. Okay, so the local errors are basically how much worse the calculation is getting from step to step. So as you go from, say, here to here, that's a local error as such. Let's get my notation right. How much extra error you pick up here is the second local error. So they're local to a point. How much you pick up here is a bit more. Okay, so obviously at the start there's no error, 0. So as we go here, look at the error is, say, the global error, or just the error in general, is the difference between the approximation and the true value. Now you could put an absolute value around that, but it might just confuse things. So anyway, so here, look at the error. You're plus 0.2 over the exact solution. That's the local error. Now we're only after one step, so the local error and the global error coincides. Now if you go again, what happens is that this time, so this is increased by 3, this is increased by 2.4. Maybe we'll just throw these in. So this has gone plus 3, but this has gone only plus 2.4. I'll just write 2.4. So this is underestimated the increase by minus 0.6. That's the local error here. Here, look, it goes plus 5. And then this one, it looks like, was it 4.1? No, it's 5.9, isn't it? So it's overestimated. It's a positive local error. And you keep on looking at that kind of a thing. So they're the local errors, the error at a single step. Now, if you add up the local errors, that's the global error. So the global error really is what we're interested in. It's kind of the difference at the end. It's just 1.2, but it's made up of the adding together all the local errors. So the global errors, you add up all the local errors. And that's where that explains all of this. So the global errors add up the local errors. And then, well, you want to get the absolute value to actually do the sums. Okay.